Welcome back to this video series on Riemann integration in higher dimensions. Before we go on with more complicated properties and more complicated integrals, I'd like to take a moment to show you how this process of upper Riemann sums and lower Riemann sums can be applied to a simple example. So here's an example to showcase that process. We'll use a very simple box. So consider the box B defined as the interval 0, 1 times 0, 1. So a box in the two-dimensional plane, and that is often abbreviated as 0, 1 squared. And we consider a function on that box to the reals defined as f of x1, x2 equals 2 minus x1 minus x2. So a pretty simple function. This function is obviously continuous, so it is Riemann integrable by what we know already. So let's try to find the Riemann integral of that function using upper and lower Riemann sums. This is indeed a very elementary way to find the integral, but I'd like to show you how this definition can actually be applied. Of course, we'll talk about other ways to compute the integrals in later videos. So what do we need to do? Basically, we need to partition that box. We need to consider partitions that we can refine. And we're going to have a look at one particular set of partitions. So we are going to consider partitions P of the following kind. Our partitions will be made up of smaller boxes that have a side length of 1 over k. So basically we use the box 0 to 1 over k times 0 to 1 over k as a template. And then we just move that box around. So we add a vector a to that, where a is contained in 1 over k times 0 to k minus 1 squared. Let me first illustrate how that looks before we move on here. Okay, so say we have this box here. Right, so that is our box that is between 0 and 1. So here's 0 here, 1 here, 1 here. That's the box B. And then we partition that box into smaller boxes. It looks like this here. Basically, that's the idea. We're taking boxes of side length 1 over k. So in this example, this is 1 over 3. This is 2 over 3, and same here. Okay, so the side length is 1 over 3. What we're seeing here is the case k equals 3 then. And the a's, so these vectors here in that example, that would then be when it started at 0. So this is one possible a. Another possible a would, for example, be 0, 1 over 3. Yeah, so that is choosing 0 from the first set, 1 from the second. That is 2 over 3 and 0. And we can also move in the other direction. That would be the a associated to 1 over 3, 1 over 3, and so on. Yeah, so this, for example, just mark this here. Here a is 1 over 3, 1 over 3, right? And that here is the box associated to that. Okay, so that's the box pinned at that point A. And now what we want is we need to compute the minimum or the infimum and the supremum of f over those boxes. Because f is continuous and those boxes are compact sets, we can actually compute the minimum and the maximum. Now if you look at f, then you'll see that it's 2 minus x1 minus x2. So it decreases as x1 increases, and it also decreases as x2 increases. And that means if we look at a box like this one here, so if you look at this box here, the minimum value of f will be attained in that corner here, right? So where x1 and x2 attains its maximal values, that's where the function f attains its minimum. Okay, so this here is where we'll assume the minimum of f of x for x in that box B, right? And the maximum, on the other hand, will always be attained at this corner here below. This is where we'll attain the maximum of f of x, x in B. So for every box, the lower left corner gives the maximum value, the upper right corner gives the minimum value. Okay, for every box in P, f attains its minimum at the upper right corner, and its maximum at the lower left corner. So that enables us to compute the upper and the lower Riemann sum. Let's start with the upper Riemann sum actually. That corresponds to the maximum, so this blue corner here is the one that we want now. Okay, so let's compute that upper Riemann sum first. It's denoted by sigma plus f on the partition P. And we just need to sum over all of our boxes in that partition. And then we need to multiply the area of the box with the function value, the maximum function value over the box. So we're summing up over all A in the partition. So it means A is 1 over k, 0 to k minus 1 squared. The area of the box is always 1 over k times 1 over k, so 1 over k squared. It's the area of the box times the function value. And we already saw that function value is attained at the lower left corner here. And that is just the point A. That's where we pin that box, right? So times f of A. So that is what we have to compute. And that's a little tedious, but not that hard to do, actually. So let's first substitute the actual function definition. Summing up of the same A, 1 over k squared times, and f of A is 2 minus A1 minus A2. Okay, let's use properties of that sum here. So first thing we can do is we can sum up over all A in 1 over k times 0 to k minus 1. That constant part here. So we just take out this 2 here. And of course we also need to take out this 1 over k squared. Okay, so that's the sum of 1 over k squared times 2. And that sum does not depend on A at all. For the second part, here's the minus. We take this 1 over k squared out of the sum. And then we are left with a sum over the A1s and A2s, and both take on all values between 0 and k minus 1. So in fact, we have to sum up overall A1 from 0 to k minus 1, and all A2 from 0 to k minus 1. Right? And we're summing up over A1 plus A2. Pay a little attention here. So actually A is in 1 over k from 0 to k minus 1. That means we still need to respect that 1 over k factor. Yeah, so that's actually A1 over k plus A2 over k. Okay. So first, this first sum here, that's pretty easy. It doesn't depend on the A at all. So we just have to count the number of summons. And well, that's 0 to k minus 1. So that's k possibilities here for each of the components of A, and A has 2 components. So that will give us k times k possibilities to select an A from that set. So that sum has k squared summons. And that means what we get here is, well, 1 over k squared times 2 times k squared. That is the value of the sum. Okay, and here, what can we do here? Well, let's also take out this 1 over k here to make things a little easier. So that's minus 1 over k to the third. And then we can divide the sum into 2 parts. First is the sum from A1 equals 0 to k minus 1 and A2 equals 0 to k minus 1 over A1. And then plus that same sum over A2. Okay, so that first term here, that the k squared cancels out, so that's just a 2. For that second part, what do we get here? Well, this first sum here, that depends only on A1, right? So it's just an A1 in here. What does that mean? Well, basically, we can also say we'll sum up over the A1 times this sum over just over 1. So we just have to count the number of summons again, and that's k summons in here. So what that is actually is k times the sum of the A1 from 0 to k minus 1. And the same argument is true for this sum over the A2s. So in this case, it's the A1 sum that is empty. And in effect, we're just summing over the A2s. Okay? Now, again, let's take out this k here. And that means what we get here is 1 over k squared. Then you'll notice this sum here is the same as this sum here, of course, yeah? So the index is called A1 in the first sum and A2 in the second sum, but the values are exactly the same. So that's the same thing as 2 times just this one sum. That is the sum. Let's just use A1 from 0 to k minus 1, A1, like this. And finally, we can use a formula for this sum here that should be familiar. So what we get here is, well, that sum is simply the same thing as the upper bound of that sum, so k minus 1, times the upper bound plus 1 over 2. So what we get is k minus 1 times k over 2. And now, of course, the k cancels out once again. The 2 also cancels out. So we're left with k minus 1 over k, which is exactly the same thing as 2 minus, well, k minus 1 over k is the same thing as 1 plus 1 over k. And if we refine the partition, meaning k goes to infinity, then this converges to 1. So the upper Riemann sum converges to 1 for this particular choice of partitions. Next, we have a look at the lower Riemann sum, and you find this is almost the same thing. So what happens here? Sigma minus of f and p. The idea is precisely the same. We'll sum up overall a in 1 over k. This time, scroll back a little, this time we need this upper right corner instead of the lower left corner. And we'll simply get that by increasing each of the components of that a by 1. So instead of summing from 0 to k minus 1, we just sum from 1 to k. So that always gives us the corresponding upper right corner. Okay. The area of the box itself is, of course, the same. And we can then also just say f of a here. So the computations that we get are almost identical. I'm not repeating those, so you can just look those up for the upper sum. We end up at something like 2 minus 1 over k to the third times 2k times, and now we have a sum a1 from 1 to k of a1. So what's different to that sum before is the sum is not from 0 to k minus 1 this time, but from 1 to k. Yeah, and of course, that gives us the following result. So what we get is 2 minus 2 over k squared. One of the k's cancels out here. Times k plus 1 over 2. So we now get 2 minus 1 minus 1 over k. And again, you can see that for k to infinity, this converges to 1. So for this particular choice of partitions, the upper and the lower Riemann sum coincide. And as we know, the lower Riemann sum is always less or equal to the upper Riemann sum for every possible partition. So we found a partition where they agree if we just refine this partition to the limit. And that actually means that must be true for every partition. Okay, so we have shown here, final result, that this integral over 2 minus x1 minus x2 dx1 x2 over the box 0, 1 squared, this integral is equal to 1. So we've shown that in a very elementary way. And in one of the following videos, we are going to have a look at less elementary ways that are computationally a lot faster than this example here. I'll see you then. Bye.